In this video, we will be finding the points of inflection of a function and then discussing the concavity of the function. The definition of point of inflection is if the tangent line to the graph exists at a point where the concavity changes, then the point is a point of inflection. There are three types of points of inflection. Notice on this first example, we have concave up here until we hit this point, and then the curve is concave down. So it changes from positive second derivative to a negative second derivative at this point. Our tangent line is oblique tangent line. This curve, by the way, is a piece of the sine curve. Another point of inflection that we can find is when we have a horizontal tangent line. This graph is y equal x cubed, and you'll see that on the left side of this point, the function is concave down, and on the right side of this point, the function is concave up. On this example, this, by the way, is the cube root of x. It has a vertical tangent line at the point of inflection, concave up on the left side and concave down on the right side. If this point, C, f of c, is a point of inflection of the graph of f, then either the second derivative at c is equal to 0, or f is not differentiable at c. So our first example, determine the points of inflection and discuss the concavity of the graph of f of x equals 2x to the fourth minus 6x squared. So let's find some derivatives. Our first derivative is 8x to the third power minus 12x. Our second derivative is 24x squared minus 12. Now we want to set that equal to 0. Let's go ahead and factor out a 12. So we have 2x squared minus 1. So for this product to be equal to 0, 2x squared minus 1 equals 0. Add 1 to both sides. 2x squared is equal to 1. So x squared is equal to 1/2. And x is equal to plus or minus 1 divided by the square root of 2. This is the same as x equals plus or minus root 2 over 2. So we need to set up our intervals. A negative root 2 over 2, and then a positive root 2 over 2. And we have an interval here, and an interval here. Now, root 2 over 2 is approximately 0.707. Negative here. and approximately 0.707. I needed that so that I could get test values in the intervals. So I can use a test value of -1, a test value in this interval of 0, and a test value in this interval of +1. So we want to evaluate our second derivative to check for concavity. Our second derivative at -1, second derivative at 0, and our second derivative at 1. We have 24x squared minus 12. And let's store -1 in for x. And we get 12. If we store 0 in for x, we're going to get -12. And then if we put +1 in, we're going to get 12. So on this interval, our second derivative is a +12. So this interval is concave up. On this interval, my second derivative is -12, so it's concave down. And on this interval, my second derivative is positive, so it's concave up. So we have a point of inflection where the concavity changes from up to down. So our point here is going to have coordinates. X is a -√2/2, and then we'll have some y value. And then on this one, our concavity changes from down to up. So we'll have a +√2/2 with some y value. I need to find out those y values, so I'm going to put this number into my original function. This is an even, so the y value will be the same for both. I have 2x raised to the 4th power minus 6x squared. And let's put our -√2/2 in for x. Divide by 2. Store x. And I get a -2.5 or a -5/2. And this one will also be a -5/2. So I have, these are my points of inflection. And I have concave up negative infinity to negative root 2 over 2. And it's also concave up on root 2 over 2 to infinity. We have concave down on negative root 2 over 2 to positive root 2 over 2.